Welcome to the last day of the Embedded Open Source Summit and our Zephyr Summit. And late in the afternoon, I'm sure there are plenty of pillows to go around and lap blankets for everybody to take a nice nap this afternoon. My name is Keith Packard. I'm a senior principal and software engineer at Amazon, but you get to listen to my hobby project. So this is something I do in the evenings because I don't do enough software during the daytime, which is frighteningly true, actually. I started this project because I needed a C library for rocketry and satellite applications. I was doing embedded software with my own RTOS because everybody has to write their own RTOS. Yeah, it's kind of a requirement, right? At the time, I didn't have a C library that fit in the platforms that I was using. All the kind of the default embedded C libraries were too large for the targets that I was shooting for. I had some devices with like 32K of ROM, 32K of flash, and consuming a significant fraction of that with newlib just wasn't really an option. Let's see. Picolibc is a C library implementing the standard C APIs and some POSIX APIs for 16 to 64-bit embedded systems. It really doesn't target 8-bit systems. It kind of runs on AVR a little bit, so who knows? Maybe some people use it on 8-bit systems. One of its chief goals here, because I do a lot of safety critical applications in space, in the area of space for satellites, we don't like things to go wrong, and we don't like unexpected execution paths to cause troubles when you're on orbit. And so I don't use malloc in any of my applications. And so the thing that I really don't want my C library doing is using malloc behind my back. And so by not actually exporting malloc at all or having any dynamic memory allocation APIs in the operating system, I can be pretty sure that malloc is not being used. So that was kind of a key requirement for me. It's tuned for small memory footprints. There are some faster code paths that you can use and add and optionally compile in, but my targets are small systems, and so I'm looking for the smallest possible memory footprint. Obviously, testability is super important in any safety critical application or pretty much any system software. And so Picolibc has a pretty extensive integrated test suite that gets run every time any commits are added to the repository. Picolibc focuses on both C and POSIX conformance. So the test suites check for a bunch of POSIX and standard C API conformance. And if you find a bug, well, I just got a bug yesterday where Picolibc was returning the wrong value from FE set round when you passed it an invalid value. And that resulted in a storm of about six commits required to fix that across all architectures from one tiny little not returning the right value when you check a function. So I'm super interested in C and POSIX conformance at all levels. So error no values, the correct exception values from functions, all that kind of stuff. Super interested in making sure that all of that is correct. Because if you've got a standard and you're almost implementing the standard, you might as well not bother to implement the standard at all. Because if your users can't count on the library to actually conform to the standard and be able to read the documentation and understand what the library is doing, then they really don't have a lot of faith in the rest of the implementation either. The current Picolibc version is 1.8.6. Their numbering is kind of random. The one basically says, oh, by the way, the API is never changing because it's got a standard behind it. Why would you ever change it? And the other two versions kind of change randomly at my whim. The API is never changing, and so we don't really have any additions or we don't have any incompatibilities ever in the library. And so, you know, kind of the semantic versioning doesn't make all that much sense in this world. It's like it's all just minor version or kind of patch version updates at this point. This version was released on the 21st of January. One of the big additions was a tableless C-type implementation. Somebody pointed out that the C-type table was 384 bytes. And if you call a couple of is blank or is ASCII calls in your application, and that pulls in 384 bytes of a static table, it's like, wow, that's a huge amount of space. And I know everybody around here, everybody in the Linux space is kind of laughing at me. It's like, what? You're worried about that? And it's like, well, yeah. I got 4K of ROM on some of my devices. 384 bytes is huge. So the tableless C-type implementation, I've got a slide about that later. We'll talk about that. But it gets rid of the table, obviously. The other thing that 1.8.6 does is kind of normalize and regularize the use of the GNU inline semantic. The GNU inline semantic is something which allows you to declare a function inline most of the time, but also provide a version of that function in the library for external linkage. So if you happen to need a function pointer, or you happen to have an application that just doesn't happen to include the header and doesn't get the static inline version of it, you can get both. That's not part of the C standard, but it is a super common part in both Clang and GCC. And it's really valuable for being able to inline things like these C-type macros. And that's where kind of where I started with it. But now it's kind of regularized across the library. So any place there's inlines in the library, this should be available as both inlines and functions with external linkage. I added somebody actually proposed an optimization to speed up buffered fread and fwrite. And I'm like, sure, we'll throw that in, what the heck? And that lets you actually do the obvious memcopy when you're doing buffered I/O, so that it's not doing a character at a time operation. So it's a bunch faster for that. More testing targets. How many of you are still using 32-bit Spark? No takers? How about Super H? Anybody excited about a Super H user? There we go. Yeah, Super H is a new supported and tested target in Picolibc. It's the library for you. You know, you laugh about all these ancient targets, and you think, why would you bother to support a C library in that? And the reality is that every one of these compilers has quirks. Every one of them exposes new parts of the library to testing that haven't been tested before. Every one of them is an opportunity to learn something about how machines work, and how compilers work, and how the language works, and how the library works. And so I like to test across a lot of different architectures, even ancient ones. Probably some of the most interesting work I did in the last year in Picolibc was supporting the 68K. The 68K looks a lot like an IEEE float machine, but it's not quite IEEE float. And so all of the little variations, minor variations in math functionality required to support the 68K, that kept me occupied for weeks. It was great. Let's see. And I finished some unusual FP format code. There's a bunch of targets that vary the size of float double and long double depending upon compiler options. There's one target that I support that that will let you use 32-bit IEEE binary for float double and long double, or just for float and double, and long double is 64 bits, and it's like, these all need to be mapped in the library automatically, so that when you call a float function, you get a 32-bit float function. When you call a double function, you get the appropriate double function. And so the library now dynamically maps all of those names into the appropriate underlying implementation using symbol aliasing. So that if you have a target like, say, ARM, where double and long double are the same size, now there's zero overhead for using long doubles in that target, because you get a symbol alias that dumps you into the double code, into the same code that is executed for doubles. So that was kind of fun. Okay, there are a bunch of tool chains where you can get Picolibc for free. I know a bunch of us use Zephyr. The Zephyr SDK obviously has Picolibc embedded in it. And that was done because Picolibc was integrated into what Zephyr uses, which is crosstool-ng. The patches that we put into crosstool-ng actually let you select at compile time, when you're compiling your application, whether to use Picolibc, newlib, or newlib nano. And that was changes that I made in order to make it easier to integrate Picolibc into crosstool-ng, so that people didn't have to choose when building the tool chain which C library to support. And that actually includes both C and C++ support, which is pretty cool. Question? Absolutely.
I assume you have automated tests. Do you assume used instructions are turned on or off when you do your floating point test?
So the question is whether I assume that fused instructions are turned on or off. The C standard says you can't use fused instructions because it gives you different answers. And so all of the math functions assume that you're not turning on the fast math fused instruction stuff unless you explicitly ask for fused multiply add instructions with those inline functions.
Some compilers are turning it on by default now. And it's not a problem.
Exactly. Clang and GCC don't turn it on by default, as far as I know. Although are people configuring it to turn them on? You get to keep both pieces when you violate the spec. Don't do that. Yeah. Oh, so one of the other fun things I got to do in the last year, actually along the same lines, was so we wanted to be able to have multiply, accumulate, and round functions in the library, right? It's a super important optimization. Well, it turns out to do multiply, accumulate, and round, I learned about the obvious technique for doing it without actually having an instruction. Use the old IBM double-double technique where you have two floating point values that add together to be the result that you want. And so your intermediate representation for your fuse, multiply, and add is these two floating point values that add together to be the correct result. And then you can round those correctly to get the result. So you do a single round. So that was fun. Kind of a fun little diversion for an afternoon. It's like, oh, wait, I bet I could use that. Yeah. So Picolibc now supports the multiply, accumulate, and round functions, even on hardware that doesn't have those, instructions, and it rounds correctly in all the rounding modes. So things you can do with a hobby project. So CrossToolNG is a super popular one. I recommend that for anybody who's trying to build their own tool chain. It's a really great place to get a nice tool chain. LLVM ARM is actually shipping an LLVM-based tool chain now, and that tool chain with Clang, and LLD, and Picolibc, they use that by default now. So if you want to use a Clang tool chain, you can just go download it from ARM, and it includes Picolibc already integrated. The GNU ARM embedded tool chain, which uses GCC, don't use that one. That one is built with the thread local storage capability in the compiler disabled for reasons beyond my understanding. It literally just takes away functionality from the users. It doesn't add any value to the environment. So if anybody has any pull with ARM to get them to go fix their stupid toolkit, their embedded tool chain, that would be super helpful. I ship binary add-ons to that to just lay in a Picolibc over the top of that tool chain. So if you're stuck using that tool chain, I actually have binaries available for you to just unpack on top of the GNU ARM embedded tool chain. You can use Picolibc. But again, just go use CrossTool or use the Zephyr SDK, which is the same. Let's see. Application build options. So you can configure Picolibc at 2 times. You can either configure it when you're building with Picolibc, or you can actually do a bunch of configuration, obviously, when you're building Picolibc itself. So actually, one of the things that was super useful for Zephyr when you want to use an SDK of any kind is you don't want to have to recompile the library to take advantage of features in the library to optimize various things. A bunch of newlib, for instance, lets you select between integer and floating point printf using linker tricks. Picolibc is the same, just a little more advanced, a little fancier. That means that all of the 2 things you can configure in Picolibc at application build time are which printf and scanf level you're using. The reason for all of this complexity is that printf and scanf are like the big functions in are typically used by embedded applications. They're super complicated, and to fully implement printf and scanf takes an enormous amount of code. I haven't even finished with printf and scanf. I still have 128-bit and 80-bit floating point support to fix. It's not standards conformant yet. But that's a lot of code. It's like 5 or 10 kilobytes of code. Oh my God, so much code. Zephyr gives you options when you're building a Zephyr applications of how much CB printf support you want. And because when you're using Picolibc, CB printf is supported by printf, that kind of falls back to also offering how much printf support there is. And they kind of go together. And there's kind of 4 levels in Zephyr right now. There is an integer only mode. which only prints out ints. It doesn't print longs. It just prints ints and strings, but it does all the formatting stuff. There's a long mode, a long mode that also takes long longs, so 64-bit values on ARM32, and prints those out. And then there's a floating point mode that prints out floating point numbers as well. And so those are the kind of the, oh, and there's a minimal mode in Zephyr as well that is like a cut down version of printf that doesn't support a lot of the fancier formatting stuff. And Picolibc has that as well. So Picolibc kind of maps the Zephyr printf modes and CB printf modes into its own printf modes, and those are actually available with the SDK using the binary version of the library, and it does that with linker tricks. The other thing you can configure at build time is which C type you're using, because the C type stuff is super easy. It's either static inline functions or static inline functions that do direct value comparisons, or static inline functions that go look up stuff in arrays. Then you can actually just, it's the code that gets put into your application is static inline stuff, so it's all done at application build time. So you can pick which of those you want. By default, if you're compiling optimized for size, you get the newer C-type stuff that's just all static inlines with direct comparisons. If you're compiling for speed, then you get the table-driven version. So some of this stuff Picolibc can kind of do automatically. When you're building the library, there's a lot more options. There's so many options, pages and pages of options. These are kind of the big areas. The biggest area is locale, language, and character set support. I still don't really know what I want to do with this. There is an enormous amount of non-Unicode character set support in Picolibc that inherited from newlib. It supports a bunch of GIS encodings. It supports all the Microsoft code pages. It has a bunch of ISO support for all the ISO 8859 encodings. And I'm like, does anybody use that? Is that even interesting to anybody? You know, does anybody use the code page translation functions that are in the library? It's like, I don't think they cause a lot of bloat in typical applications, so I haven't removed them yet. And then there's language and locale support. The locale support in Picolibc is pretty thin. It supports the C locale, because we all love the C locale, right? Yeah, which made it super easy when somebody asked me if I could add the option to have commas between the groups when you're doing printf, to put commas between every 3 decimal points. I'm like, absolutely, that's super easy, because in the C locale, the separator there is the empty string. So in the C locale, you don't get commas. So all I have to do when I see that option in the printf string is ignore it. Very simple. Obviously, there's a bunch of standard I/O options. There's even more printf and scanf configuration bits. You can turn on and off whether it supports the new binary output thing. You can tell whether it supports the POSIX positional parameters, all that kind of stuff. The fast buff I/O is selectable. It's usually on by default because it's only used when you're using buffered I/O. And then there's the big option. There's actually a whole separate legacy standard I/O implementation from newlib. I haven't deleted it yet. It used to be there because the tiny standard I/O that Picolibc added didn't do everything. But at this point, the tiny standard I/O is actually more standards compliant than the legacy standard I/O. The legacy standard I/O is a ton faster though, because it's only buffered I/O. It doesn't support unbuffered I/O like the tiny standard I/O stuff. So I don't know if I should remove it or not, because I can imagine some people really need the performance of super fast standard I/O, or they want to be able to take advantage of the libstd and C++ standard buffered versions. I don't know. Maybe there's some reasons. So there's a whole pile of code just sitting there. It's like, I don't think anybody's using this. For the math library, there's a couple of interesting options here. Normally, Picolibc is built in just IEEE mode. And in IEEE mode, all the math functions only set exception flags. So if you do a divide by 0 or an overflow or an underflow or any of those invalid operations or exception generating options in the math library, by default Picolibc just sets the exception flags and moves on. So if you're running on a soft float environment where you don't have any exception flags because there's no register to stick them in, you don't get any indication of an error at all. There is error support in the library, and you can conditionally compile it in. It isn't compiled in by default for most of the builds that I do because it adds a bunch of code, and almost more importantly, it adds dependency on error that you probably don't want. Error is one of those, things from the distant past that were like, why did you pass error status back from the operating system in a global variable? What were you thinking? So, Zephyr has error support, and it's all per thread, as it should be. And you could use that error support in Picolibc, and it works if you enable it. But I kind of like the IEEE exception mode better than the error stuff, so that's what's turned on by default. There's also some new floating point code that was added like 5 or 6 years ago. ARM shipped a bunch of better math functions for things like sine and cosine. The problem with that code is that the 32-bit floating point primitives are implemented in terms of 64-bit floating point operations. So if you call the sine function with this code, it takes your 32-bit value, expands it to 64 bits, does some 64-bit math, and then packs it back up in a 32-bit value and hands it back to you. And if you're on a machine where 32-bit and 64-bit floating point operations are the same speed, like every ARM machine, every 32-bit ARM I've ever visited, oh wait, not that. But there are a bunch of machines where 64-bit operations are the same speed as 32 bits. Taking advantage of the additional precision makes things go faster because you do fewer operations to get the desired precision. You don't have to do so much fiddly extra fix-ups to get those last few bits done. The problem is that all of my targets, and I suspect most of your targets, are like Cortex-M4. That only has 32-bit floats. And so if you use the new ARM code on that target, oh wait, now we're going to go do soft floating point for these primitives. So I don't know why that code was pulled into newlib from ARM. I don't know what it's for. I don't know what ARM target is interesting to use with that code. But it's still there, and you can ask for it, but it's not used by default. It's also less accurate. New code, less accurate. The mysteries of the universe. Okay. So this is a new change. The old C-type code is obviously kind of the classic design. The reason the C-type code was implemented this way is super simple. It's really small per use, but almost more importantly, it's table-driven, and so you could use C preprocessor macros and not evaluate the parameter multiple times. And back in the pre-NC, pre-inline days, you really had to have that as the implementation. You couldn't evaluate the parameter multiple times because a lot of people do, while is blank of star b plus plus. And if you evaluated that parameter multiple times, you would completely wreck the code. And so they used the table-driven mechanism to be able to reliably evaluate the parameter exactly once. The table is at least 256 bytes. At least, I say. Because signed char is a constant problem. I just learned earlier this morning that the Linux kernel now makes sure that chars are always unsigned. They actually force char to be unsigned on all platforms so that the code is the same across everything. And so you don't get variations across platforms. I think that's an interesting question for the Zephyr community. Should we do that too? Should we adopt, because on ARM, chars are unsigned. And on x86, chars are signed. And it's like, most people often use chars with 8-bit values, assuming that it's an 8-bit value, and they're not expecting negative values. So, from a consistency perspective, I think there's a lot of value to be gained from thinking about that. To support signed chars with this old C-type code, this is great. They actually have a 384-byte array. That's actually 385 bytes. And they take the character value, add 1, and index into this array, which is offset 128 bytes into the actual start of the data. so that if you have a negative value, it goes backwards and pulls out the correct C-type information. It's like, that's a cute hack. Yeah. C-type, by the way, is not defined to operate on negative values. It's designed to operate on unsigned characters or EOF, -1 for EOF. So that is an invalid usage of C-type, and yet the new lib code that Picolibc inherited is like, yeah, but people do invalid things all the time. Let's protect them. I applaud that. That's definitely the right plan. The old C-type code supported all the 8859 code pages, all the 8859 encodings and all of the Microsoft code pages, but it didn't have any Unicode support. I don't know why. One of those mysteries. It has lots of tables, but it was like missing the obvious tables for Unicode. And so it's got value because if you're doing different encodings, that's the only way to get different encodings, because in different locales, because it can actually switch which table you use based upon the locale. And so the table-driven stuff can actually go fetch the table out of the locale and look up the value from the table, and all that's relatively straightforward. With direct comparison mechanisms, there's just no way you could support multiple locales. So the old code is still useful if you're using locales. The new C-type code is the obvious implementation, right? It's just using inlines. You have static inlines that just directly compare the provided character value against the appropriate ranges. It has a nice integer declaration for its parameter, because that's the correct declaration. And it means that all the problems with negative values, that all evaporates, because we're just doing comparisons on values, so all of them work correctly. It only works in ASCII, C locale. We love that. It uses GNU inline, which is a semantic supported in GCC and Clang, not supported in some other compilers. So if you're using other compilers, all of the inlines evaporate, and you're doing external linkage functions for all of these operations, which kind of sucks. It's selectable at application build time, and if you compile for size optimization, you get this stuff by default, and you get the table-driven stuff if you're compiling for speed, because it is a lot faster. Or if you want to actually statically declare which one you use, you can just define this variable before you include ctype.h, and you get whatever you ask for. Pretty simple. Let's see. Floating point fun. This is I was talking about the new sizes, and this is a deeper explanation of that. So C defines float, double, and long double, but it doesn't tell you what they are. We love C. It's our favorite language. Yeah, it's great, isn't it? Machines that Picolibc supports support all of these different types. Oh, and there's extra ones here that I didn't list. So 32-bit, 64-bit, and 128-bit IEEE binary, 80-bit IEEE extended, 128-bit double-double. It's got very limited support for those. And it also supports the 80-bit M68K types as well, which are not quite IEEE, and the M68K 64 and 32-bit types, which are derived from their 80-bit types. Compilers are free to map them however they like. Most compilers have a static mapping. I think with the ARM compiler you can actually tell it. I think you can probably tell it that you want doubles to be 32 bits. There's probably a GCC option for that, because I know there is for AVR, for instance. You can tell AVR to make doubles be 32 bits. Super convenient. And so now all the math library code in Picolibc is it's got, well, the 32-bit code is always assumed to be float. And then the 64-bit code is either double or long double or not used at all. It's never float, fortunately, not so far. And so the 64-bit code has to kind of switch between being the long double code and the double code. And so it's all this hairy parametric function names and macros everywhere to make sure that you land in the correct function when you have a double data type, whether it lands in the 32-bit code or the 64-bit code. Right, and I mentioned there I'm using symbol aliasing, so it's free. Symbol aliasing is there's kind of like two different ways to do it, and the newlib had used this old technique where it actually used inline ASM in the source code to do the aliasing. It actually had an inline ASM that had a .equ in it to do the aliasing. I'm using the attributes now and the GCC pragmas to get the aliasing to work correctly. That fixes a bunch of problems on systems that prepend underscores to their symbols. Thank you. What system was that? There's some embedded target for which the ABI still prefixes underscore on global symbols. Thank you. I don't remember which one. Might have been Spark. I don't know. One of those. Using the compiler is obviously the right way to do that, because then the compiler sorts it out instead of having to sort it out myself. So at this point, Picolibc has pretty complete support for all 4 of those data types, 32, 64, 80, and 128. It has a tiny amount of support for double-double. Anybody know? Anybody experience the delights of IBM double-double? Yeah, it's a wacky representation. So this was IBM's plan to do extended precision math. It's basically you take two floating point values, and the real value is the sum of these two, and the rule is that the exponent for the right side one has to not, the significand doesn't overlap at all. You make sure that there's no overlap in significand, and so you shift stuff around to make sure that they don't overlap, and that they sum together to be the actual answer. And there's pretty straightforward rules for doing addition and multiplication and subtraction on those. And it all kind of works, except that you have this weird variable precision, because the smaller exponent may be way over here. And so it's really hard to understand what it means to do rounding, or to do what's the error value of this function. It's like you have variable precision. Not my favorite, but PowerPC uses this by default. Oh. Yeah. So there's a tiny amount of support for that in Picolibc. Pretty much, it's got rounding functions and classification functions like isinf and isnan and that kind of stuff. And it has square root, because square root wasn't too bad. But don't ask me to do any of the more complicated intrinsics. Let's see. They're mapped at library build time and uses symbol aliases. I should review my slides before I give a presentation, shouldn't I? A lot of this stuff was for AVR. AVR pretends to be a 16-bit platform. It's really an 8-bit platform, but it pretends to be 16 bits. And somebody got excited and came in and said, can we use Picolibc on AVR? It's like, AVR has a pretty good C library. It's really small, nice for your tiny targets. And they're like, yeah, but we want to use and I got a bunch of patches. And I'm like, okay, your name is not Jiantan? Good to go. That joke's not going to get old for a while, is it? Yeah. Let's see. Okay, so one of the biggest motivating factor for me actually doing a bunch of work in the C library was standard I/O. I struggled with trying to find a competent standard I/O for my embedded systems forever. The number one thing is it has to be standards conformance. Printf is frickin' hard to implement, and it's got a lot of options and a lot of niggly details, and applications depend upon it doing what it says on the tin way more than they should, because there's a lot of corner cases here that you can get wrong really easily. Obviously, I want to avoid malloc, because my systems aren't going to ship with malloc, because when malloc fails on orbit, what do you do? Yeah, actually you don't even crash, because you're still in orbit. You just kind of go quiescent and die. And it's like, oh, more space junk. Great. Yeah. So I found this awesome algorithm, the RIOT floating point printf algorithm. It is standards compliant. It is not the same as what most printf implementations do. Most printf implementations, to be standards compliant, use thank you, use arbitrary precision arithmetic in the middle of printf. With mallocs, the whole 9 yards. So you're printing a floating point number. It's like, oh, we're going to go malloc a giant pile of memory and do some arbitrary precision arithmetic for 10 minutes. This algorithm is all fixed precision, but it is standards conformant. And by standards conformant, I mean that if you print a value, you get a value which is the closest possible decimal representation in the number of digits that the maximum number of digits that it can present. And then when you read that value back in, you get exactly the same bits you had before. So it's round trippable. And that's kind of the most important attribute of that. It does not give you the, if you ask for 100 floating point digits, glibc will actually keep printing digits all the way out to the 100th digit, getting closer and closer to the decimal value of your floating point number. This code doesn't do that. It's like, yeah, we're going to print out 17 digits that is enough to represent the value, and then you get as many zeros as you asked for. Standards compliant, does what it needs to do, and doesn't have to do arbitrary precision computations. Let's see. We only got about 4 minutes left. I think I'm going to skip some of this stuff. I talked about the buffering. So Picolibc uses a buffer-free API. It means it has getchar and putchar for every single character in and out of the library. That's super slow. One of the cases that I've discovered that is really common for people to be using this for is snprintf just with %s. And the reason that people use snprintf with %s is they don't want to use str_ncopy. They replace str_ncopy with that. Why would they do that? Anybody know why they would replace str_ncopy with snprintf? No, the reason you replace str_ncopy with snprintf is snprintf guarantees that result will be null terminated. str_ncopy does not. So it's a nice fix for a library bug. We have better fixes available, but that's a really common paradigm that I've seen. And using Picolibc for that it sucks. It's really, really slow. The other problem with standard I/O is that the size of the file struct, it varies depending upon which kind of file struct you're using. And that's kind of problematic. It means that you can't use freopen with things like standard in. I don't know how to fix that and still meet my memory budgets, so maybe it won't get fixed. Let's see. I think I can see, oh my goodness. I'm going to talk about some Zephyr stuff. Picolibc is now the default library for Zephyr, so if you're using the defaults these days or you're using Zephyr head, you'll be using Picolibc. You can either use Picolibc out of the Zephyr toolchain, the Zephyr SDK, or you can use it out of a Picolibc module and actually build the library at the same time you're building the application. You need to use the toolchain version if you're using C++ because the toolchain has to be compiled against the ABI of the library, and so you can't use the module version of Picolibc. So there's a bunch of options you don't get in customizing Picolibc. You can't get if you're using C++. But after I added the printf stuff to make sure that you could, customize printf, most of the need for that went away. So it's pretty cool. You can actually use C++ and libstd C++ and Picolibc in your Zephyr applications. It all works just fine. And here's a couple of examples of how to build it and how to run an example. To configure stuff with Zephyr, you can configure the printf and scanf level. Those are automatically configured by your CB printf stuff, or you can go in and customize them in the Picolibc bits. You can also set the malloc heap size. I may have made a mistake here in the default configuration. Picolibc uses the same malloc that the minimal C library does now. Exactly the same code. The only difference is that when you select Picolibc, the default heap size is different, and that's probably a mistake. With the minimal C library, the default heap size is 0, so you don't actually have a malloc heap. I don't know why it's 0, but it is 0. And with Picolibc wanted to make it useful. It's like, well, why don't we just use all of the available RAM that isn't used by anything else for the malloc heap? It's pretty easy to compute. Well, it didn't turn out to be that easy to compute. And it causes some occasional linker adventures. So probably not the best possible plan. Maybe we should switch it back, but maybe it's too late now. If you want to customize Picolibc at a finer level of detail than is provided by the C-type and printf stuff, you can go in and use the module, and it's got half a dozen options. It's not as customizable as the upstream Picolibc configuration because there's a bunch of stuff that just doesn't make sense for Zephyr. So it's pretty limited in that way. But yeah, how many of you have actually discovered that you're using Picolibc when using Zephyr? Yeah, a bunch of people. Very cool. Very cool. I'm going to end here, leave a little bit of time for questions. Thanks so much for coming this afternoon. I know it's late in the afternoon on the last day, and what we all want to do is go get some dinner and go to bed. Oh, wait, maybe some people want to do other things, but that's my plan. I have a microphone if anybody has questions. Oh, more microphones.
Right. So my intuition with alternative car sets, like things beyond, is that it would take a fair amount of space. But you mentioned that it wasn't that big actually to support the alternative car sets.
So by alternative character sets, I mean things like the Microsoft code pages and ISO 8859-N. Those are both byte encodings, and so their tables are 256 bytes or 384 bytes in the case in the Picolibc case. So they're not huge. Now, if you ask for the GIS character encodings, those tables are enormous. They take like 30 or 40 kilobytes to do just to Unicode mapping and back. So they're pretty expensive. You have to ask for them, and they're not available by default. And you don't get them, of course, until you call the functions that need them. So we could build them into the library and make them available and just never use them. And it's pretty inexpensive. What gets expensive is when you add the locale support and all of the standard C functions that used to just have direct inline stuff now have to go out and check to see what's up with the locale. And the NewLib has support for locales, but the only real locale support it has is when it's being used in Cygwin. So it has acres of locale support, none of which work in anything but Cygwin. So all the embedded targets for NewLib just get the C locale. But it still has all this locale code and all this locale conditional stuff. I need to kind of figure out what makes sense to keep using in Picolibc. It's still kind of, I haven't spent the time to kind of figure out what locales mean in an embedded environment. So you can have character sets without locales, but a lot of the usage of character sets is tied to locales.
May I also have a question, or? Yeah. First, Keith, thank you so much for all this work. Quite amazing for hobby projects. Somebody do that full time and do much less. No, seriously. So, what is behind the corner or around the corner? So, what do you plan for next months, years, or you don't have any plans?
I don't really have a lot of plans going forward. I'm watching, right now, Synopsys is doing a bunch of evaluation with a proprietary C library test suite that they have access to. I'm expecting to see a lot of bugs coming out of that, which is super exciting. Bugs are good. Bugs mean you're finding problems. So I'm excited about actually getting bug fixes for those and adding tests that uncover those bugs. As I said, I still have some printf and scanf support for really long floating point values that I need to add. Right now they're approximated. They're not round tripping. They're just doing the old school floating point math to kind of try to generate approximate digits. So I've needed that to do. Other than that, I have a PR submitted on Zephyr right now to fix the fact that the malloc heap is always included in every application. So I'd love to get some review on that. I think it's one of 2 outstanding PRs I have in Zephyr. So if anybody wants to review my PR, I'd love to have that get reviewed. But in Picolibc, I don't know. Anybody have any? I have a bunch of stuff I would love to do, but kind of my biggest project is something that's really big. I want to go rewrite the math library. The math library has a bunch of precision gaps that have been uncovered over time, and it would be nice to actually go in and fix it. One of the nice things we have with modern computers is that we can actually enumerate all 32-bit floating point numbers and run them through functions and evaluate, exactly how precise all the math functions are. And somebody has done that and actually has numbers about Picolibc precision, which is how we discovered that the ARM functions were less accurate than the old Sun functions. And so I would love to go in and rewrite all that stuff. That's a really big project because I need to actually do the math to understand how those polynomials are generated. I've read about a dozen articles on that, and so far it's not sticking in my brain yet. If anybody knows how to generate Chebyshev polynomials for the intrinsic functions of the math library, do it and provide me code. That would be great. Otherwise, I'm going to have to learn it myself. You had a question?
Are there any instances for embedded that you wouldn't recommend using Picolibc?
In instances for embedded that I wouldn't, no, of course not. Picolibc is the best. Probably on AVR processors, 8-bit AVR processors, where Picolibc is so standards conformant that it's actually significantly larger than the AVRC library. The AVRC library still has, its math library is much less precise than even Picolibc's. And so maybe you don't want to use it, but I use the AVRC library whenever I'm targeting those processors. Other than that, it's Picolibc everywhere. I think that's enough questions for one day. Thank you so much.
Thank
for
you,
coming.
Keith.